So let's now talk about power, and especially the power in an electric circuit, which is our interest here. So generally speaking, we can use the energy concepts in many different situations. So in the context of electricity, what we have is a source of energy, which is a battery, and that battery is going to convert chemical energy to provide energy to the moving charges, the electrons, and it gives them that energy in the form of potential energy. That potential energy will then be used by the charges to convert into kinetic energy as they move through the circuit. And when they go through a resistor, that kinetic energy of the moving charges is going to be transferred to the surroundings, that is to the atoms of the resistor. And that energy is basically going to be dissipated in two forms. One is going to be light in the case of the light bulb, and the other is heat. So the environment is going to be heated up by some of the energy dissipated by the resistor, and that energy is coming from the electrons that are passing through, and they get their energy from the battery. So there's basically a transfer of energy from the battery to the electrons and then to the surroundings in the resistor. Or the light bulb in this example, but it can be something different. It can be a computer, a TV, any electric appliance that will do something for us is going to convert energy into something else, and very often there's also some heat dissipated into the environment. So going back to the definition of power, power is defined as a ratio of work done over time or energy delivered or provided over time. Those are the same units, so we can talk about work or energy. Both of those are measured in joules, and the time is measured in seconds. So the ratio joules over seconds is what we will refer to as a watt. That's the energy of power. Now in the context of electricity, there is a more direct way of computing the power either provided by a battery or used by a resistor, and that is the product of voltage times current. So in the case of the battery, it would be the voltage provided by the battery multiplied by the current delivered by the battery to the circuit. In the case of a resistor, we would multiply the voltage across that resistor by the current that's going through the resistor. Either way, we would end up with voltage times current, and so if we use volts for the voltage and amps for the current, we end up with a measurement of power in watts. And so as you can see from this, if either of these quantities increases, then the power increases as well, and if both increase, then you have an even greater increase in power. Now let's switch over to series connections. So first let's talk about combinations of resistors. So we can have two basic combinations. Those are the ones we'll be discussing here. There are more complicated cases, but that's beyond the scope of this course. So first we have connections in series, and that is what happens when we connect light bulbs one after the other. So this light bulb is connected to the next one, which is connected to the next one, and all of that is eventually connected to a battery. That's what we refer to as a series connection. By contrast, we also have a connection in parallel, where the three resistors are connected to each other. So here you can see wires connecting those resistors to each other, and that combination is connected to the battery right here. So that's a parallel combination. And then later on in this video, I'll talk about a combination of series and parallel connections. So first, the series connection. So here, when we have three resistors in series, there are a few rules that will be applied here. One is that the same current goes through all resistors in series. Second is that the voltages of the resistors add up to the total voltage of the battery. And then the rule for the combination of resistances is a simple addition. So you add up the resistances of the resistors and you get the total resistance. So here's that in an example. So in this example we have three resistors, 10 ohms, 15 ohms, and 5 ohms. They're connected in series, just like in that previous picture. And all of that is connected to a 6-volt battery right here. So the questions are, what is the total resistance of this combination? What is the total current? And what is the voltage across each resistor? So the total resistance, as I said, is the straightforward addition. So 10 plus 15 plus 5 gives you 30 ohm resistance. Once we have that, we can figure out the total current by taking the voltage of the battery and dividing that by the total resistance. So 6 for the voltage over 30 ohms gives us 0.2 amps. Once we get this, we can figure out the voltage across each resistor. Remember now that each of them is receiving the same amount of current. That's the total current. That's the 0.2 amps. So we can call that total current. We can also call it current through number 1, number 2, and number 3. They're all the same. So the voltage across resistor 2 then will be 15 times 0.2, which makes it 3 volts. And for number 3, it's 5 times 0.2, which makes it 1 volt. And you should verify that 2 plus 3 plus 1 adds up to 6 volt as it should, which is the voltage of the battery. Let's take a look at the parallel connection then. So in parallel, the resistors have the same voltage. So unlike the series where we had to add up the voltages to get the voltage of the battery, in parallel they all have the same voltage there, and depends on what is connected to that, but typically that would be the voltage of the battery. Then the current through each resistor is going to be different because it will be that common voltage divided by the resistance of each resistor, and those things can vary. But then there is a rule that connects all of them, and that is that the total current has to be the sum of the individual currents. We'll see that again in an example in a second. And then the rule for the total resistance is a little more involved than the one for series. So we don't just add up R1, R2, and R3. What we do is add up the inverses of those things, and then that gives us the inverse of the total resistance, which means at the end we will have to invert that number to get the actual total resistance. This is usually a potential for mistakes in the calculation, so pay extra attention when you get to this step in your calculations. It's pretty easy to make a mistake or overlook something here. So here's an example of that. We have 3 resistors, 20, 60, and 5 ohms. They're all connected in parallel to the voltage of to the battery, so that's a 6 volt connection. And so first question is, what's the total resistance of this combination? So the way we find it, as I said, we take the inverse of these things, so 1 over 20 plus 1 over 60 plus 1 over 5. You can do this 2 different ways. One would be a pretty simple approach. Grab your calculator and take the inverse of 20, the inverse of 60, and the inverse of 5. You add them up, you get 0.2666. This is a little exaggerated, but I just wanted to have more digits than necessary so I can get a nice rounding of the value at the end. And then when I take the inverse of this, so 1 over 0.2666 gives me 3.75 ohms. Another option, which sometimes works, it's not always the best way of doing things, but with fractions you can also add up the 3 fractions. So what you would do is find a common denominator. So here we have 60 as a common denominator. We could have chosen something else, but 60 is probably the lowest one. And then we need to multiply each of the fractions. So the first one gets multiplied by 3. The second one we just multiply by 1, we leave it untouched. And the third one we multiply that by 12 to get 60. 5 times 12 is 60, so that's how we get the 12 here. So altogether this gives us 16 over 60. And then don't forget we need to invert that, so 60 over 16 turns out to be 3.75 ohms, exactly the same answer as here, and there shouldn't be any difference. Okay, so that's just for the total resistance. The next thing we want to do is find the total current. Well, once we have the total resistance, we find the ratio of voltage of the battery over the total resistance, and that gives us 1.6 amps for the total current. Then, if we want to know the voltage across each resistor, we take the common voltage. Remember that those 3 things, the 3 resistors, were connected together, so the voltage across this one, or that one was always equal to 6 volts. So when we get to computing the current, we just take the voltage 6 volts, and then we divide it one by each of the resistances. So 6 over 20 should be 0.3 amps. 6 over 60 should be 0.1 amp, and 6 over 5 should be 1.2 amps. And when you add them up, you'll see that 0.3 plus 0.1 plus 1.2 gives us the same thing as the total current, which is 1.6 amps. So everything is good here, and we've answered all the questions.